So we looked at module 2 where we saw that there was a PF1 had to flash at a certain frequency. We verified that it works, but we used a logic analyzer to do it. So in module 9, we'll take the same code, which is the main that we have here, and we'll modify this main so that we can work with a technique of inserting what is called instrumentation. So in order to do that, I will open a new project, which is my lab 9 project, which is this one, and I added a few lines to it. So the lines that are borrowed from the example from C9 are the delay routine, which is exactly as it was before, and the crux of the main is still the same. So I'll show you what that part is in just a second. So this is the main that hasn't changed, where I have a call to port F in it. So we'll switch to our lab C9, module C9, which will have the code that we saw from module C2, which is the delay routine and the main. So I'm adding a few lines to the main that involve the instrumentation. So first, let's identify the code that hasn't been changed. So this is the code that is still the same, which is my while loop here, my port F in it, which is still the same. These 3 lines, which involve reading the LED, toggling it, and the delay line, which calls the delay. So this part has not been changed. Now what I'm going to add to this code is these 2 declarations, which will be my arrays that I'm going to declare. One of them will hold the time and the other will hold data. And what we also see is because I'm calling this the SysTick, I'm going to call SysTick init. And so I'll show what SysTick init does in just a second. I'm going to index the array, so I'm going to use I, which is going to be my index, so that I can write to it. And the 2 times that I grab from SysTick are going to be in last, and it'll be in last and now. So these are the 2 points where I grab the values. And then I take the difference between these 2 values and write it to, this is the difference, which is appropriately masked because it's a 24-bit number, and I write it into the time array. Similarly, I take the value of what I'm actually reading or writing to the PF1, and I put it into my data array. So there's going to be 2 arrays. So there'll be 2 arrays. One will be, like as I said, my data array. The other will be a time array. So the data array and the time array. And the time array is going to contain, both of these are going to have 50 elements in it, index 0 through 49, 0 through 49. And in each iteration of this loop, I'm going to be writing. So these 2 statements here are the 2 statements that will write to those 2 locations. And then I change my I from 0 to 1, and then I write into the next location and the next location and so on. So in all, I'm going to be writing 50 values into the array. So let's take a look at our SysTick init. So I'm going to quit out of this. So let's look at our SysTick. And we see that the SysTick is a pretty straightforward init. All we have is the 3 registers of interest to us, which are our control register, are which is the control register, which is right here, the reload register, and the counter register. So I declare them so that I can access them. And then my initialization process is first to disable the counter. I disable the counter by writing a 0. And then I initialize the reload value to the maximum possible. And then I write 0 to the counter so that it becomes its clear set. And then this part here does 3 things. This one does 3 things, which are disable interrupts. So disable interrupts, start counter, and select clock, the clock source. So by writing the 5, I'm doing that. So we'll debug this code in simulation first. So I'm going to hit the debug button, which will load up my view here. And to this, I'm going to make sure that I can open the watch window. So I say watch 1, which will show me the time and data arrays. And I'll show that in just a second. So I'm going to dislodge this from here so I can see it better. So I move it out of here. And I'm going to go ahead and run this. It'll run for a certain amount of time. I notice that the LED is changing values. And then I stop it. And I look at the data array, which shows me the hexadecimal value of data, which is 2 and 0, 0 and 2, 0 and 2, which is turns on and turns off. And there'll be 50 such items here. And then there is my time array, which shows me values, which are the first value is 32, the second one is 159996. So I'm going to do this. I will select that, and I'll open a calculator, and let's paste it there, and let's multiply this because this is SysTick, and remember the SysTick runs at 62.5 nanosecond tick time. So I multiply that, and then I divide it by, because it's nanoseconds, that is 10 to the minus 9. So I'm gonna put 9 zeros there. So it tells me that it's 0.09999, which is pretty close to 0.1 seconds. So the nice thing about using this technique is that we don't have to have any special equipment. Now, we can also notice that this technique works if I were to switch from simulation to the real board. So I'm going to change this. I'll go to the debug and choose the board. I say OK. I turn on my board, and I will rebuild the target and flash it again. So it's going to load it. It's done. It says download code to flash, and I'm going to run it now. And this time when I'm running it, I will again have the same interface, and now I'm going to go ahead and say run, and it's running. It's going to do some number of flashes. I can see the LED flashing on the board that is connected to it. Now I want to verify whether the time is right. So I'm going to go here, stop it, look at the time, and I see some value here. And so I'm going to choose this. Let's go ahead and check whether this is correct. So I'm going to paste it here, multiply that by 62.5 nanoseconds, divide that by 1,0,0,0, that's 9 zeros, and it's 0.09, so it's not quite accurate. It should have been a little higher for us to be close to 0.1 seconds. So what went wrong? Well, we can figure that out, because what happens is on the board, this time to do this loop where we decrement, it takes less time on the board compared to the simulation. So maybe this number is wrong. So maybe I'll change this. What if I change this to something appropriate? Maybe I'll change this to 16160. So I'm going to comment that out, and I'm right now testing to see whether I can get a more accurate value. So I save that, I quit my debugger, and I load it. And let me build it first, because I modified it. Build it, load it, re-execute it, and now we will run it and see whether there's a change, a significant change in our value. So I'm going to stop it. It's flashing right now. I stop it, I look at the data, and I see a number that I'm going to copy and again paste it here, multiply by 62.5 nanoseconds, divide that by 169 zeros, and I get a 0.1 nanoseconds with some small error. So this kind of confirms to me that my estimate of this number here was appropriate in simulation, but it was not appropriate for the real board. Now, we've kind of not only debugged it, we also figured out a way to fix the problem, because debugging is not only finding where the bug is, but also finding a fix for it and then verifying that your fix has in turn made a difference and rectified the problem.